Alright guys, it's been a while since I haven't posted any video, but I want to start off with this CSEC question. It's a 2013 January past paper question. So the first question that we want to start off with, as you're seeing here, it says to describe a test to show that semiconductor diode is defective. Of course, I think you guys would have learned about semiconductors, right? They are simple devices that lies in between a good conductor and a good insulator. The semiconductor diodes can be used to do several things, and so for that reason, we just want to check to see when it is defective. Uh, with this question, it can be a very tricky question. So the answer that I would give in relation to this is to check, right, to see if the diode is able to rectify an AC current, all right, into half wave rectification. So that's kind of like probably the easiest way. Rectification, right? I think by now you know that diodes can be used to rectify AC current, right? And what we mean by that, AC current looks like this, right? It alternates back and forth, and so on. Now, if we were to set up a circuit, right, we could connect a diode in the circuit, which would look something like this. This is your AC current. That AC current is then connected to some component, possibly, let us say, we could put a resistor here, and then after the resistor, we could then put a diode. But that diode must be in forward bias, right? Must be in forward bias. So to be in forward bias, I think this is how it would have to be connected. Let me just verify. Negative to positive. No, that's not the way how I would connect it. Actually, it's the other way around. This method is in reverse bias. So if I turn the diode around the opposite way, then it makes it in forward bias. All right. This is our diode. This portion of the diode is the positive end. This part is the negative end. Whenever we have the negative and the negative connecting, that's when the diode is in forward bias. If we were to connect an oscilloscope right here, we should get our output wave looking like this, right? We should get our output wave looking like this. So to just check if it's defective, then you wouldn't get this as the answer or as the output if the diode is defective. So that's pretty much one way to which we could look at it, right? Or we could set up a circuit, of course, that switches between a forward bias and a reverse bias configuration of the diode, right? So there are two general modes through which a diode can be in. It can be in forward bias or reverse bias. Now, as you're seeing here, this is when the diode is in what we call forward bias, right? That is simply when the positive terminal. Let me use a battery in this case, right? It's when the positive terminal is connected to the positive side of the diode. I must just say that a diode acts as a switch in most cases. So if the diode is not acting as a switch, then it therefore tells us that it is defective. How we know if it's not acting like a switch is when it allows current to flow in both directions, meaning that if I were to change the polarity of the battery, in the sense that if I had negative here, positive on this side, right? If current is still flowing in this way in which the circuit is set up, then this will tell us that the diode is defective, because no current should flow, no current should flow in reverse bias, right? Now, as I said, this is forward bias. That is when current is going to flow. So it allows current to flow, allows current to flow in one direction. Hence the reason why we get this as the output. All right. So that's, in a sense, just explaining what is happening here pertaining to this. All right. Now, with all of that being said, let us look at the other question, right? That says sketch the IV graph for the functioning semiconductor device. Now, as you know, there are characteristic curves or graphs that shows us ideally how different components should operate. So for this case, we're considering the diode. Now, as I said, remember the diode symbol for the diode is this, right? Now, diodes are widely used in electronics. A typical LED is a diode. So you must know this, the circuit symbol for that. This is just a pure diode that we're looking at. And the characteristic curve tells us how it actually works. I'm going to show you quickly how it actually works. Right, so typical graph like this, if we wanted to sketch the characteristic curve, um, the diode in itself is one that operates like this. Right? This is typically the characteristic curve as we are describing it here. This is, we could consider here to be I, right? We could consider this side to be voltage. So basically what is happening here is that before the diode is able to conduct or to allow current to flow through it, there must be a minimum voltage that the system must have, or the diode must receive a small amount of voltage before it can actually turn on. It would almost come in like you wanting to start up a machine or something. You would have to give it a little bit of maybe heating first or something of the nature to boost it in a sense. And possibly when you reach to the sixth form level, you'll understand why this is the case, right? Now, I could explain it to you. Now, when we think about semiconductors, they don't really allow electricity to flow as easy as you can imagine. So you need a little bit of energy, right, in order to excite the electrons in the valency band, in order for them to jump over to the band gap where conduction will take place, right? So when you see us applying a small voltage here, it is to give these electrons energy so that they can jump across the band gap, so that they can conduct, right? So that's the purpose of this. Now, what we are seeing here, whenever this happens, whenever we have this portion of the graph here, this is explaining forward biasing, right? This is explaining forward biasing, and as we said, that is when the diode is conducting perfectly. However, on the negative portion of the graph, we could actually allow the diode here to actually conduct. It could actually conduct current or allow current to flow in a sense, but it would mean that you would have to apply a lot of voltage, right, which would ultimately destroy the operation of the um the diode, such that it forces current through it. So if you increase the voltage up to maybe about negative 50 volts or so, right, that in itself could damage or break down the operation of the diode, such that it allows current to flow through it. But as you can see, it requires a lot of voltage to do that, right? And whenever that happens, we are within the portion of what we call the breakdown voltage, right? So that particular voltage that causes current to flow in the forward biasing position tells us that it's called the breakdown voltage, and so on. So that's kind of like what we're describing here in terms of the curve. You can get 2 marks for this if you were able to simply draw it and possibly label it and everything. So as we said, that in this region is the reverse biasing, right? And we don't really expect it to operate, but if we exceed the breakdown voltage, then we expect it to pretty much conduct. Now, to just stop off this question here, that is to draw a simple truth table for a NOT gate, right? NOT gate is quite easy, guys. So NOT gate has one input. So the symbol for that is, it looks similar to that of the diode, right? So in terms of its input, it can have only 2 possible combinations, right? Quite easy stuff. So whatsoever the input is, right, it's going to give us the opposite, right? So that would be a simple 2 marks right there. Quite easy, eh? Yeah. So it says draw and complete a truth table for a NOT gate, and that would just take you right into that. Now, to finish off here, we want to look at the continuation to this question that says, we should find or calculate the equivalent resistance of these resistors in series. Clearly, we are seeing 3 resistors in series, so we can go ahead and, of course, use our formula that says RT is equal to R1 plus R2 plus R3, and this continues to R equal N, so it doesn't matter really, because we can have several or multiple resistors there. Now, for this, we'll just go ahead and put in the values, right? Right, and we're seeing here that the answer is going to be 24 ohms. Right, that's our answer here. Now, using the same resistors, we connect them in parallel. Looking at this, they are connected in parallel, guys. So please don't watch how the wires actually shape or so forth. It's actually in parallel. Now, in parallel, once we have more than 2 resistors, then we have to use this formula to say 1 upon RT is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon Rn, etc., etc. It continues. So for this case, I must also say that we can use another formula if we had resistors that have two. If we only had 2 resistors, we could use this to say RT is equal to the product of over the sum. So the product would be R1 times R2 divided by the sum of that. Of course, you could still use this to find RT. You just have to just find the inverse of the answer really. So this is what we're going to do now. So 1 upon RT is equal to 1 upon 2 plus 1 upon 6 plus 1 upon 12, right? Simply, this can be somewhat easy. You just go ahead and find the LCM. LCM will be 12, right? 2 into 12 goes 6. 6 times 1, 6. 6 into 12, 2. 2 times 1, 2. 12 into 12, 1. 1 times 1, 1. So what we're left with here is 9 upon 12. All of that is still equal to 1 upon RT. Now, please bear in mind that this is not your total, what do you call it, total resistance as yet. So we're saying that 1 upon RT is equal to 9 upon 12. To find RT, we could cross multiply if we want, right? But in this case, we just find a flip because it's the inverse, so we just flip it, right? So RT is equal to 12 upon 9, which corresponds to 4 upon 3, which corresponds to 1.33 ohms. So that takes care of that answer. So if you do that perfectly and do it correctly, you get 4 marks. Easy marks to get on your exams. Now, the last part of the question says that last year for Christmas rather, Paula had to put together a set of bulbs to light her family's Christmas tree. After much thought, she decided to put together strings of light in series. It says, was this a wise decision? Justify your answer. All right. So, firstly, in order to be able to answer this question, we must remember, the advantages and disadvantages of series, in a sense, series circuit. So, it's not a wise decision. So, no, not a wise decision. Right? And then now, of course, you need to state the reason. And that reason would simply be that if one light, right, burns out, or in other words, in our Jamaican terms, we say if the light bulb blow, right, then the remaining, right, light bulbs will not turn on. And we know, say, when it comes on to Christmas bulb and so forth, or them type of thing there, see, it if it's quite obvious that they will blow over time. So if you connect all of those bulbs in series, if one of them break or one of them blow, right, or go bad, then pretty much the whole entire thing not gonna turn off, it's not gonna work. So you wouldn't want to do that, Zine. So that's one of the reasons. Now, also in series, right, the voltage is divided, right? Since the voltage is divided, what we have come to realize is that the light bulbs are going to get dimmer, right? Dimmer each, right across the amount of light bulbs per se. So can you just imagine having 100 light bulbs and the brightness is dimming or getting lower and lower each time, or the intensity of the light is getting lower and lower each time? Then that is not going to make the whole thing be effective in the sense of you wanting a Christmas tree to operate and everything like that. So that really takes care of this answer in a sense, right? And it should be able to can give you 2 marks. Let me see if I can think of anything else that could possibly. Now in series, right? The total, if we look back at the previous question, we're seeing that in series circuit the resistance is very high. So if the resistance is very high in a series circuit, then it shows us clearly that there's going to require a large amount of current to allow the bulbs to operate. And also, if we look at a parallel scenario, we're seeing where the total resistance is much less. So therefore means we require less current to flow in the circuit and all of that. Hence the reason why in a parallel scenario it will better able to keep the light bulbs going and keep it at the right brightness. If one light bulb goes out in a parallel circuit, then everything will continue to work because they operate independently of themselves. So that's really what we have to share here in relation to this question.